Earth orbits, from low Earth orbits to geostationary. You'll be required to calculate such things as, given an altitude, calculate the period, or perhaps the radial velocity, or the other way around. Given a period, calculate the altitude, as well as know some basic applications for the various orbits, their commercial uses. All right, so with Earth orbits, if we start at the bottom, we talk about low Earth orbits. Earth orbits are also sometimes referred to as geo-orbits, and also not to be confused with the orbit of the Earth. We're talking about orbits that surround the Earth. So low Earth orbit is anything from sort of 200 kilometers up to 2,000 kilometers. So 200 kilometers. This is altitude. Up to 2,000 kilometers is referred to as low Earth orbit. Now, if you recall what we often lazily refer to as Kepler's law, although it's not truly Kepler's law, it's Kepler's law if you assume that their orbits are circular and that you assume Newton was correct, then you get this particular expression. And so you may be asked to find such things as, well, what's the radial speed of an object in a low Earth orbit? Now, you may already know these things are fast. They're moving incredibly quickly. So we expect to find something of the order of kilometers per second, perhaps. Let's see. All right, so before we can do any of this, we're going to need some of our stats. So we've got the 6.67 by 10 to the minus 11, and not that we need to be terribly familiar with the units, although you could be asked to work them out. Pi, of course, is 3.14159,265 and a bit. We're going to need the mass of the Earth, 5.972 by 10 to the 24. Of course, that's kilos. That's not light. And we're going to need the radius of the Earth, because the orbits are given in terms of altitudes, and as with all things in physics, we calculate things assuming that they're point sources. So we need to convert altitudes to center from the distance from the center of the Earth. Radius of the Earth then is 6.371 by 10 to the 6. And of course that is meters. So my value for the low Earth orbit must be the 2000, so 2.0. Let's not be too strict with significant figures. That's 2 by 10 to the 3 meters, plus the distance that the surface of the Earth is, or the average radius of the Earth, 6.371 by 10 to the 6. Now, I've screwed something up already. I've written 2,000 kilometers when I need to write 2,000 meters. Let's fix that. Kilo is 10 to the 3. 2,000 is 10 to the 3. It's got to be 10 to the 6. And so that is just 2 plus 6 is 8. 371. by 10 to the 6 meters. So this is the effective radius of an object that's at 2,000 kilometers, so the very top of the low Earth orbit. And you might be asked, well, how long does it take to get around? Well, if you rearrange your equation, it's t squared, so I just need the square root. I have 4 pi squared on top, plus I would have been multiplying by r cubed, and that'll be over this thing. Some people like to memorize this as a constant. Sure, why not? I'm far too lazy for that. And assuming I used my calculator right the first time around, which is not easy, right? That's probably the second hardest thing in physics, is to use your calculator. Entering all the exponents and bits and pieces is not easy. 7625, and of course the SI unit is seconds. That's about, is it just over 2 hours? It's about 2 hours by the look at that. So these things rip around the Earth at this orbit once every 2 hours. And if they're in the lower Earth orbit, of course, it's less than that. So quite quickly. And now that I've got the distance taken to travel a circumference, I can easily find whatever that radial velocity must be, radial speed. I need the distance around the outside, which is 2 pi r. And my r I found to be 8.371. Not that the significant figures are that important for the illustration of this point. Over, so distance on time, so 7, 6 to 5. So the distance around the outside of the circle divided by how long it takes to get around. And that comes out to be 6898 meters per second. That's fast. That's nearly 7,000 meters per second, 7 kilometers per second. Fast. Compared to us, of course. And truly, because of the universality of relativity, there's no such thing as fast or slow, but compared to us, that's fast, 7 kilometers per second. Just so we've got some idea of how fast that is. Quite quick. All right, and so some of the things that the low Earth orbit then is used for, well, we haven't talked about energy yet, but you can imagine that the energy required to get something into low Earth orbit, which is at 2,000, compared to something at a higher orbit, which might be 20,000, 10 times that particular height, is less. It takes much less energy. Less energy, less fuel, less cost. And so it's cheap. It's cheaper to put things in low Earth orbit than it is to put them into a higher orbit. So it's cheap. And this is because of, the delta E required is less, which implies less dollars. All right. What do you put there? Well, there are all of your surveillance satellites exist here. Of course, you want them closer to the Earth so you can actually see. Now, these aren't responsible for creating the images that you see on Google Satellite View. That's a lie told to us by Google. They're actually aerial photos taken by an aeroplane. Surveillance it's not nearly as higher resolution as that. The International Space Station exists here, the ISS. Write it out. International Space Station. You can imagine if you want to ferry people and goods up and down, back and forth, you want that to be in a low Earth orbit. The rickety old Hubble Space Telescope is in this. I shouldn't speak disparagingly of the Hubble Space Telescope. We're told the James Webb Telescope is meant to be its spiritual successor. However, the James Webb Telescope, it looks more at the red end of the spectrum. Hubble looks across the visible and peaks either end, peaks into the ultraviolet and the infrared. James Webb goes deep into the infrared, and Hubble, whilst it's sitting in a low Earth orbit, the James Webb Telescope is going to be on the other side of the Sun, sitting at a Lagrangian point. So I don't quite understand how it's billed to be the spiritual successor. I mean, James Webb was due to launch in 2010, I think. Still not there. It's 2020. Next year, maybe. Next year. All right, so the Hubble Space Telescope sits there. Not that this occurs much anymore, but all of your manned space flights, of course, were to low Earth orbit. A biggie, most of your communication satellites sit within this band. Of course, Elon Musk is in the news. He's trying to build here a constellation, a group of satellites, or a set of satellites called a constellation. Trying to put his Starlink, is it called? Polluting the sky with his satellites for the purpose of blanketing the Earth in internet coverage. So communication satellites, of course, you need a lot of them to cover the Earth, since they're all moving at different speeds. And interestingly enough, you'd think, well, if they're moving around, does that slow things down? Actually, it speeds things up. When the nodes are moving around in a communications network, it actually increases the throughput if it moves from node to node. And having them in lower orbit reduces the latency. Of course, we tend to be quite sensitive to latency if we're doing things like real-time communication, or if you're playing a computer game online, for instance. So you want those to be as low as possible. So if you want to service the entire Earth, you put them into low Earth orbit. And you have a lot of them. Let me just tidy up the notes here. Come on, select. No. Oh, good. Good. Did I get everything? Hopefully. Let me just put. So these are all applications. What's bad about it? Well, you're still within the upper atmosphere of the planet. The Earth's atmosphere does peter out quite quickly, but it's decreasing exponentially, and so its effects drag on for quite some distance. So you end up with orbital decay. I should say orbital decay. Orbital decay. due to upper atmosphere. So this implies these things need to be regularly replaced. They burn up and fall out of the sky, or their orbits decay. Generally, these are cheap enough that you can deploy them in great number. They don't have any kind of maneuvering ability, because that would be a large, expensive satellite that would eventually exhaust its fuel anyway. So these things, you throw them up, and when they fall down, you throw more of them up. And so these LEO satellites are short-lived. And the length of the lifetime depends, of course, on the altitude. So the low Earth orbit, really low ones, you may not even get a year out of those guys. Higher up, you get several years. They need to be replaced. I shouldn't write so close to the edge of the page. Need a page, I need another page, insert page, thank you. All right, so that's low Earth orbit. Now, the next set of terminology mid-Earth, I'm making that up. Higher than low orbit, mid-Earth higher orbits. And the main ones here are, the main thing you should be familiar with are the positioning satellites. So I'm going to write them. I'm going to mention three. There's lots of them. Of course, if you're a large nation state, you don't want your positioning system. You don't want to have to be reliant on the positioning system of another large nation state. So the GPS, the global positioning system, which is put in place by the US military, conducted by the US military, cost them about $1 billion a year. Not cheap. And originally, when they put these up, they retarded the signal or encoded or in some way limited their accuracy that was available to civilians. The rest of the world, they've since opened that up, but they have no guarantee of service. There's no guarantee of service with the GPS, especially during wartime. So if the US goes to war, they can pull the pin on this whenever they want to, which of course makes the Russians uncomfortable. 2,200 kilometers up. Now that's coincides with what is known as half a sidereal day. And I should define what a sidereal day is. A sidereal day is the time taken for the Earth to spin around once. And you might think, well, how's it different to a day? Well, a sidereal day is a little bit shorter, because after the planet spins around once, it's no longer facing the sun directly, or you wouldn't be if you're on that particular point where you were 24 hours ago, because the Earth has shifted in its orbit. And so you get one extra day. The Earth gets one extra day simply by the fact that it goes around the sun. So a sidereal day is 23 hours, 56 minutes, 4 seconds. So the global positioning system is set at that altitude to be half a sidereal day. Probably makes mathematics a little bit easier. There's no great reason it has to be there, and just because I guess they're Russian. The Russians stuck theirs, GLONASS. I don't actually know what that stands for. It's probably Russian. Is just a little bit lower, sneaks in underneath it. 100 kilometers. And the Europeans are building the Galileo. Not sure what the N stands for. Satellite system. Galileo navigation satellite system. I'm making that up. You'll have to look it up. But anyway, the Europeans have stuck theirs, the EU, at 23,222 kilometers up, so just above GPS. How these things work is actually quite fascinating. You need at least 3 of them in order to get ideally, if everything worked perfectly, you'd need 3. In practice, you need 4 of these satellites to be above you at any one point in time in order to get a position. And what they're sending is pretty much just the time. They send the time down, and your device calculates their difference in time and triangulates that in a 3-dimensional space. The reason you need a 4th one is because the clock in your device isn't terribly accurate. And so the more of these satellites you have, the better your satellite lock, your GPS lock is. A modern device will use several of these at once. So it's not just we say GPS, people will talk about GPS like it's a thing, but your phone in your pocket most likely connects to all of these, if not more. The Chinese are building one as well. And I've neglected to chase up what those stats are. I'm not sure the Chinese one's finished. The Galileo one's not finished either. But these things can still work even though they're partially finished, even if they don't have a full set. All right, so next up, when we get really far out and being important, are the geostationary. And geosynchronous orbits. There's a slight, a subtle difference there. Geosynchronous, S-Y-N, chrono. Oops, my U doesn't look very convincing. Geostationary, geosynchronous. That's worse. At this altitude, if you put a satellite up there, it takes 1 sidereal day to orbit the Earth, and so it effectively stays above the same spot on the Earth. Now, that's true if it's at the equator. If it's not at the equator, it still takes 1 day, 1 sidereal day to get around, but it's no longer geostationary. It'll effectively move north and south as you look at it from the Earth, back and forth, north and south. And so that will be what we call a geosynchronous orbit. So it's not stationary, but its timing is 1 sidereal day. At this place, you put weather satellites or communication satellites that only service the one area. Let's try and work out what that altitude should be. So let's write the period, as I've been saying, is 1 sidereal day, which is 23 hours. There's no standard notation for hour, by the way. 23 hours, 56, nor the minute. 56 minutes, 4 seconds. And that's 1 sidereal. EAL? EAL. I think it's EAL. Sidereal. I think that might be true. I'll have to check it afterwards. Sidereal. I think that's right. It's just one sidereal day. And converting that to seconds is 86,164 seconds. And we need all the stats that we had before. We're going to need, again, I'll just repeat them here so it saves me having to scroll back and forth. The mass of the Earth, 5.972 by 10 to the 24 kilos. I need to radius the Earth to subtract away from whatever I find. Because this time I'm interested in finding the altitude. So 6.371 by 10 to the 6 meters. Of course, we need universal, gravitational constant, 6.67 by 10 to the minus 11. That should be enough to get me there. So if I took what we call Kepler's law, I need the cube root. A little neater if I do that way. And so 6.67 by 10 to the minus 11. Mass of the Earth, 5.972 by 10 to the 24. Time is that 86,000 seconds, 164. What have I done wrong? Something's not right. That guy. That guy. Yeah, that looks better. That's going to look better. And 4 times my pi. Let's not show off now. 4 pi squared. And that'll give you about 4.22 by 10 to the 7 meters, right? So if you're asked to calculate this, many students will quote that as their answer, but of course that's not the altitude. The altitude is this one minus the radius of the Earth. Ooh. Lag in the iPad, thank you very much. 4.22 by 10 to the 7 minus what we wrote down earlier, 6.37, well, 1, whatever, times 10 to the 6, 3.58 by 10 to the 7 meters. All right, so that's 36,000 kilometers. We're told the given value is actually $35,786 kilometers. So the altitude of the geosynchronous orbit, or the geostationary orbit, is 35,786 kilometers, so 36,000 kilometers up compared to 2,000 here for this guy and 20,000 for this guy. So we're at 35, so not quite double the GPS, which is already considered a very high orbit. So this is a long way up. A long way up. It's expensive. Because the delta E is huge. The amount of energy you need to get things to that altitude is a lot, which implies that huge dollars. And so applications. If you have a communication satellite, that only services the one area. And so early on in the history of satellites, there was a big battle to get your communication satellites into this particular low Earth orbit, because you could spend a lot of money on one or two satellites and cover the majority of your country. Australia, I can't remember the name of them now, had 3 of these expensive satellites that are put up. I think they're controlled by Optus now. Forgotten what they're called. Yeah, the trouble being is the latency up there and back is quite large and unacceptable for most communication services. And if you have a problem with one of these satellites, fixing it is expensive. You've also your weather satellites. If you want your weather satellite to only service your particular area, you might put it there. But again, I can imagine cheaper, more modern weather satellites being closer, simply because of the difficulties that I mentioned earlier. It's expensive to get there and they're difficult to repair. Yeah, I can't think of anything else. Communication satellites and weather satellites that only service the one particular area. Interestingly, there's a story about the Queen of Tonga, who at some point owned 3/4 of the geosynchronous orbit. I can't quite remember how the story goes, but through a keen piece of legalese, she ended up in control of a lot of this, and so the Tongan government, or she, made a lot of money out of this, selling off space. Interesting. Okay. So that should do it for this particular lesson. Just to recap, so the kinds of things you'll have to do is, maybe if you're given a particular altitude, to find a period or a orbital velocity. Or likewise, if you're told what the period will be, then to calculate what the altitude should be. And you need to be familiar with what the commercial uses are at these various altitudes. All right, well, that's the end of this lesson. I've been Keith Johnston. Thank you for watching.